Thank you for participating in the National Program 211 Water Availability and Management Listening Session. I am Kevin King, Research Leader at the Soil Drainage Research Unit located in Columbus, Ohio. Over the next few minutes, I am going to highlight some accomplishments from the Midwest area. Mapping tile drain lines with drones. ARS scientists in Columbus, Ohio, in collaboration with university partners, proved that unmanned aerial vehicles, drones, are an effective means to map agricultural drain lines. Due to economic and environmental considerations, better methods are needed for mapping subsurface drainage systems in agricultural landscapes. Knowing the location of subsurface drain lines provides us a means to estimate drainage density and intensity and develop metrics that can be related to the water balance and water quality. Many of these drain lines were installed prior to global positioning system technology, so there is no record of where their exact location is. Drones equipped with visible, multispectral, and thermal infrared cameras can be employed to map drainage systems in large farm fields. After a large rainfall event, the soil over a drain line is dewatered sooner than the soil between the drain lines. Consequently, good UAV drainage pipe mapping results are often achieved a day or two after a large rainfall. As an example, the image on the left is a contractor's as-built map of the subsurface drainage system. The center image shows a UAV thermal infrared orthomosaic map of the field one day before a 3-inch rainfall. The image on the right shows that same field obtained one day after the 3-inch rainfall event, where the drain line pattern is clearly depicted. Unmanned aerial vehicles are an effective means to map agricultural drain lines. Enhanced bioreactor for nitrate removal. ARS scientists in St. Paul, Minnesota showed that low temperature performance of wood chip denitrifying bioreactors is improved by dosing with carbon or by using agricultural residues. Spring season tile drainage nitrate losses are significant, and cold water temperatures hinder nitrate removal in wood chip bioreactors. Dissolved carbon addition to the wood chip bioreactor inlet increased nitrate removal by 10 times at a temperature of 42 degrees Fahrenheit. Using corn cobs rather than wood chips increased nitrate removal by 4.5 times at a temperature of 35 degrees Fahrenheit. These findings highlight that cold temperature bioreactor performance can be improved, as well as reducing the footprint of the structure. Preferential flow and hydrological transport mechanisms. ARS researchers in West Lafayette, Indiana, investigated and quantified preferential flow and hydrologic mechanisms of nutrient transport. Trend analysis of precipitation patterns across the western Lake Erie Basin revealed increasing rainfall amount and intensity over the past 40 years, with field-scale hydrometry showing that these rainfall patterns and associated antecedent conditions control subsurface tile flow generation. Multi-tracer laboratory and field experiments elucidated sources and flow pathways of water and nutrients to subsurface tile drains, especially the components and contribution of preferential flow. Subsurface phosphorus placement, as either incorporation with tillage or direct injection, was identified as an effective management practice to decrease phosphorus transport to subsurface tile drains. These findings not only help to explain current observations in the tile drainage systems, but they can be used to inform, develop, and improve current nutrient transport models, as well as help to choose the most efficient best management practices for reducing nutrient losses to surface waters. Dairy manure management. ARS scientists in St. Paul and Morris, Minnesota showed that dairy manure management practices reduced tile drainage nitrate losses. Using a 160-acre tile drain silage field, the researchers were able to show that reducing manure application rates and fertigating during the growing season, as opposed to injecting in the fall, reduced nitrate nitrogen concentrations and loads in tile drainage water. Specifically, fertigation reduced nitrate loads by 22%, and the soil nitrate concentrations in the soil at depths of 30 to 90 centimeters were reduced by 47%. Furthermore, these results were achieved without decreases in forage production. Development and deployment of phosphorus removal structures. ARS scientists in West Lafayette, Indiana, and Columbus, Ohio, developed, improved, demonstrated, and disseminated phosphorus removal structures throughout the Midwest. Research and testing was conducted in order to ultimately increase efficiency and decrease cost of phosphorus removal structures, which aim to filter dissolved phosphorus from agricultural drainage. This included laboratory-scale research dedicated to studying phosphorus removal mechanisms, as well as field-scale construction of over 10 units throughout the Midwest. Structures were designed to remove 40% of the cumulatively dissolved phosphorus load over a lifespan of 5 to 25 years and is dependent on the site. The Natural Resource Conservation Service has adopted this practice into their cost share program, Standard 782. This work also impacted the use of blind inlets, as it was demonstrated that blind inlets could be converted into phosphorus removal structures in a cost-effective manner. P-Trap software was created and released, intended to allow non-engineers to conduct a site-specific design in a timely manner and a cost-efficient manner. Chemical application setbacks safeguard water quality. ARS researchers in St. Paul, Minnesota, evaluated the effectiveness of chemical application setbacks to reduce the off-site movement of chemicals with storm runoff. Management of turf grass on golf courses and athletic fields often involves application of plant protection products to maintain turf grass health and performance. However, the carrying of fertilizer and pesticides with rainfall runoff from the area they were applied to neighboring surface waters can enhance algal blooms, promote eutrophication, and may be harmful to sensitive aquatic organisms and ecosystems. Experiments with water-soluble tracer compounds confirmed that an increase in application setback distance by 6 meters resulted in a 43% reduction in the total percentage of applied chemical transported with the storm runoff to neighboring areas. Application setbacks offer turfgrass managers a mitigation approach that requires no additional resources or time inputs and may serve as an alternative practice when buffers are less appropriate for land management objectives or site conditions. No-till combined with cover crops mitigated excessive transport of dissolved constituents. ARS scientists in Columbia, Missouri showed that no-till combined with cover crops and a longer rotation or a precision agricultural system maintained crop yields obtained with minimum tillage and mitigated the disadvantages of no-till alone for the transport of dissolved nutrients. On claypan soils, which have a restrictive layer that impedes infiltration and increases runoff, there is a trade-off between erosion control and transport of dissolved pollutants. No-till reduces erosion and sediment losses, but it can double or triple losses of pesticides such as atrazine and dissolved phosphorus. Scientists in Columbia, Missouri have shown with model simulation studies and long-term surface runoff monitoring that when no-till was combined with cover crops and a precision agricultural system, these losses, that is atrazine and dissolved phosphorus, please note the graph in the middle, were similar to those of the baseline system, a minimum till system. Crop yields were maintained as well. Sediment losses were reduced by 85%, the top right graph, and nitrogen losses by 40%, the bottom right graph. On these soils, combining multiple practices was necessary and successful to avoid trade-offs between erosion and the transport of dissolved pollutants. Conservation practices in the South Fork Iowa River. ARS scientists in Ames, Iowa, documented the adoption of conservation practices in the South Fork Iowa River. The top right graph shows mapping of conservation practices. For instance, the grassed waterways are the dark green lines. The diagonal green stripe show land treated, that is, receiving runoff by the grassed waterway. Water and sediment control basins, many terraces, are in purple and terraces in orange. Lower graphs show adoption of conservation practices over time. These are also derived from aerial photographs. The data are shown in decadal increments. Individual conservation practices are identified along with the years of establishment and removal. Note that in 2010, installation of grassed waterways is balanced with the amount of waterways removed. In the 1980 to 2000 timeframe, we saw installation of wascobs, and these are replacing some grassed waterways as they are easier to farm around. Grassed waterways are the most common conservation practice. Furthermore, net amounts of conservation practices has changed very little in the last 20 to 30 years. Quantified nutrient balances and water quality impacts. ARS scientists in Columbus, Ohio and West Lafayette, Indiana, along with university partners, quantified nutrient balances and water quality impacts from crop production and conservation practices from the Eastern Corn Belt. The reeutrophication of Lake Erie has resulted in a call for a 40% reduction in phosphorus loads to the western basin of Lake Erie. Using an edge-of-field network located on private lands throughout northwest Ohio, the researchers were able to show that field balances for phosphorus were near neutral, that is, inputs near equal to outputs. This SEEP and LTAR related accomplishment showed cover crops to be effective at controlling erosion and significantly reducing nitrogen losses in tile drainage. The effects of cover crops on phosphorus loss were uncertain. Drainage water management, the practice of artificially raising the outlet elevation of a subsurface tile outlet, was shown to be effective for reducing nitrate, nitrogen, and phosphorus in tile drainage. However, the effects on phosphorus loss may be negated by potential increases in surface runoff and subsequent phosphorus transport. Implementation of the 4 R's of nutrient management, that is, the right source, rate, time, and placement of fertilizers, was demonstrated to reduce phosphorus loss. Specifically, when applied at equal rates, there was no difference in losses between organic and inorganic sources. Applying at university recommended rates reduced phosphorus loss risk. Greater phosphorus losses were measured when rainfall occurred within 5 days of application, and placing fertilizer below the soil surface significantly reduced phosphorus loss. The Soil Vulnerability Index. ARS scientists in Columbia, Missouri, and other ARS and university cooperators evaluated the accuracy and the usefulness of the Natural Resource Conservation Service Soil Vulnerability Index, which characterizes a soil's vulnerability to loss of sediment and nutrients from cultivation. NRCS developed an index to classify cropland vulnerability to erosion and losses of agricultural inputs. The index is called the Soil Vulnerability Index and is based on SERGO soil properties. NRCS's goal is to include this index as one of the tools used to streamline assessment and delivery of conservation needs across the nation. This accomplishment is in cooperation with SEEP. ARS scientists in Columbia, Missouri evaluated the Soil Vulnerability Index at 13 ARS SEEP watersheds across the United States. Findings included strengths and limitations that alert planners of when they can have confidence with the SVI rankings and when they should take caution. An outcome of this is the frequent request of NRCS to ARS to explore adding factors in the Soil Vulnerability Index that relate rainfall amount and intensity, as well as the inclusion of a restrictive layer in the soil profile. While there are many other accomplishments associated with water management and availability in the Midwest, I hope these give you an appreciation of the types of research and research capacity housed within the ARS units located within the Midwestern United States.